All right. It's always fun to do the talk after the party, isn't it? We're all a bit worn and torn. And I got up early to revise this whole deck because I keep changing my mind about how we're actually going to do this. It's not an easy thing to do. My name's Richard Campbell. I've been making podcasts for a lot of years. Any .NET Rocks listeners? Oh yeah, awesome. A few in the room. So you'll know we're at 1883 as of today, or is it? Yeah, yesterday. And I've also made a couple of other shows as well. But this is really .NET Rocks based because a few years ago, it's actually going back as far as 2011, Carl talked me into doing these shows called Geek Outs, which I didn't think was a good idea, and I was wrong. Really just exploring different topic areas that I thought was interesting, and I wasn't sure that anybody else would think was interesting. But back then we were making 3 shows a week, made a lot about sponsorship, and so I would put out one a month. Since we're down to 1 show a week, I feel like we still have to kind of talk about software development once in a while. So I've sort of confined myself to sort of end-of-year recaps on the state of energy production on the planet and the sort of state of space. And those often get asked to be turned into talks as well. And if you were here last year, you know I did a future of energy with a UK spin where I talked a bit about how the UK's migrating. You guys actually turned off all your coal power plants. Like, that's cool, right? So lots of evolution there. But yeah, the Geek Outs, there's about 100 of them. I'm still making a few. But the trouble really started with this when I did the moon-based Geek Out in 2017. So this was based on a European Space Agency paper that I'd read that really was talking very practically about how a base could be established on the moon for science, much like Antarctica. So periodically occupied. And a set of experiments they wanted to do, things go over. It was a paper effort. European Space Agency doesn't spend anyway. Let's be clear. ESA spends more money than the UK does, but not a lot more. So they were hoping the Americans would jump on board. So I did that podcast, and then NASA called, which is a pretty good day. And to be clear, actually, they wrote me an email, and I was very skeptical at first because NASA.gov, sure. So I end up on the phone with a guy named Chuck, and Chuck says, "Listen, we really like your podcast." I'm like, "Oh, that's nice. That's cool." It's like, and he only knows me as a podcaster. He doesn't know what else I do. So he says, "Would you ever consider doing a talk, about the moon base?" I'm like, "Okay." He's like, "Do you know PowerPoint? We like PowerPoint at NASA." I'm like, "Yeah, Chuck, I know PowerPoint." Kind of know PowerPoint. He goes, "Well, if you'd be willing, we'd love to have you to talk." I'm like, "Okay, well, who do you want me to talk to?" He's like, "Well, us." Like, NASA? Yeah. It's your stuff, right? I kind of got it from you. And he's like, "Yeah." Like, so you want me to talk to you about your stuff? It's like, "Yeah." All right. So that fall, I got to go down to NASA Ames, which is one of their main laboratories south of San Francisco. And when I drove onto the site, there was my name. My mother is proud. It's pretty weird to drive to a NASA site and see your face in lights. And so it was a good talk. Had a lot of fun doing it. I've done it a bunch of other times. Then it turned into a presentation. And before that, I hadn't done these things as presentations. They were just podcasts. So you're now seeing the latest incarnation that started with this lineage. When we talk about being a spacefaring civilization, the first question you got to ask is why? Like, as if we didn't have enough problems, why do we want to introduce more? The first and easiest answer to that is hey, you know how the dinosaurs went extinct? They didn't have a space program. So we actually have, in this world today, between the European Space Agency and NASA, a group called Planetary Defense, which is a pretty cool business card. And they actually talk about a lot of weird stuff, but obviously one of them is tracking asteroids. It's not the only thing they do. These are the same guys who prepared a paper to say, how would we stop a supervolcano from erupting? Answer is put a lot of geothermal power plants around it and suck all the heat out and turn it into electricity. It's kind of clever. But their main job obviously is the asteroid thing. And by the way, they have made progress. If you've been following what's been going on recently, there was the DART mission where they actually did an experiment where they deliberately collided with a small asteroid, Diddy Mouse, to see if they could alter its orbit. And the answer is yes. It actually worked better than expected. It's a relatively small vehicle. I think this is an animation of yes. So that's so this is actually a binary system. There's a larger asteroid and a smaller one. We're going to hit the smaller one because it's in orbit of the bigger one. That way we don't cause any real problems. All it's going to do is get closer to the bigger asteroid if it works. And so this was a series of photographs taken of the impact, which is about 500 kilos, moving it somewhere in the neighborhood of 6,000 kilometers an hour towards the little rock. And it gets, you start to see some detail in here. Little rock's half a frame. There we go. That's the frame that didn't make it because some drama happened. Anyway, did a good job. The goal, the previous orbit had been about 24 hours that the little moon went around the bigger asteroid, and their goal was to change it by a few seconds. They were hoping like 30 seconds or so, and it actually shifted it by half an hour. So one of the things they realized looking at the debris was that this asteroid, like many, are just a rubble pile. They're just lots of little rocks sticking together with minimal amounts of gravity. And so when you hit them, they bounce against each other and you actually communicate a lot of energy. And it speaks to a possibility of us being able to alter trajectories fairly reliably. But it's going to depend on composition. It's going to depend on overall mass. Something like the Chicxulub crater causing Beast, that's going to be pretty tricky to move because, that's the size of a continent. And, you're not going to be able to hit it with a little asteroid. That's a bit tricky. And arguably, developing this system, while a logical step in the right direction, it's still very much a preventative measure. So you don't want to wait until we can see that there's an asteroid in a particular collision to go, okay, well, we have to gear this up and take our experiments and try to implement them. It would make more sense to actually be good at this by making it a viable business. And that's where we get into this idea of, can we start extracting resources from asteroids? Because if we can do this, one of the ways to stop the thing from hitting us is to turn it into iPads, It was going to destroy the world, but instead it increased the economy. There's also a case for, we are already getting pressure as we have been able to pretty much tame this planet and do plenty of damage to it along the way. We're starting to run down the easily accessible resources in certain class, especially rare earths. We've been enjoying a period in our civilization where we're utilizing a larger amount of the periodic table than ever before. But we're also finding that while there are some easily extractable versions of those materials, there are many more that are very difficult to extract. And so there's an asset paper where they talk about, we are in about a 50-year window of, if we don't get to a place where we can start to collect these specialized materials, rare earths and the like, from the asteroid belt, which we need to go into space, as well as for things down on Earth, we likely won't. Because as the price starts to go up, you won't waste it on space when you're going to need it on Earth. So unless we actually have those resources coming from the rest of the solar system, we probably never will. So it's kind of a time limit. Again, speculative paper, not everybody agrees, but then why would they? But it does speak to, right now, we have this opportunity. So on one hand, we have planetary defense. It's a good idea for us to protect this planet, not just from asteroids, but the rest of the ways that we're wrecking it. But also an opportunity to create new resources, to expand our civilization, to have access to more in general. I would also point out that, generally speaking, humanity has a certain number of explorers. They're the crazy people, and it's good to send them somewhere else, right? Now, we're in England, so you were used to exporting crazy people to the New World. Worked pretty well. They got crazier over time. But this is another option for that. And it's not just that you be able to move those folks off and give them something interesting to do. It's that the stories that they tell are a part of us all. That our civilization is better when there is a frontier being pressed against, to inspire, to explore on, to generate new technologies, to create some ideas, and to go a bit further. So that's the justification. Let's talk about the bits we need to get better at. And obviously, we have to start with getting into orbit. And Heinlein has this great quote of, once you get to Earth orbit, you're about halfway to anywhere. Still true. Now, We're going to always battle against science fiction and science fact here. So a lot of folks are, this is only going to get really practical to hang out in space if we have things like space elevators, which is a great idea, that we would actually run a cable from the surface of the Earth up to geostationary orbit. We're going to need a bit of a counterweight when we get up there. We have to make one of the strongest materials ever thought of to actually have that strip exist. We think we found materials like that in the form of carbon diamond nanotubes, except for that part where we can't actually make them larger than a couple of microns long, and now we need a 40,000 kilometer one, several million of them actually, and they better be perfect or they'll break. There's also other interesting problems. You pretty much have to put this on the equator because it is going around. If you put it anywhere else, you're going to have some dynamics problems. It's 40,000 plus kilometers long, so how fast is that car? You're going to have to go a little bit faster than a regular elevator. You're not going to go thousands of kilometers an hour, but maybe hundreds. But that also means that the journey up is days. So, pack a lunch. Hopefully there's seats. And you're also going to go through the main part of the Van Allen belts along the way. The Apollo astronauts had to go through the Van Allen belts, but they did that in a high inclination orbit, so they went through the smallest parts of the Van Allen belts. They also were booking it when they did it, about 27,000 kilometers an hour. So they spent about 4 or 5 minutes transiting the Van Allen belts. You're going to spend the better part of a day. Bring your lead underwear. And it may not be necessary. We're at an interesting time with rocketry. Our buddy Elon has been working really hard on this particularly nutty rocket. It doesn't work yet, but his proposal is a fully reusable rocket. It's now the largest rocket ever built. It's 9 meters in diameter. The first stage of the Saturn V was 10. So that's a little bit bigger, but then it got smaller. This is the same size all the way up. The volume on it's unbelievable. We've had 2 flights. Both have resulted in rapid, unscheduled disassemblies, but that's what test flying is about. The progress from Flight 1 to Flight 2 was remarkable. Flight 1 was kind of a train wreck. It destroyed the pad, the rocket didn't complete separation, it was all over the place. The second flight, that's 33 engines burning perfectly, which a lot of space folks said was impossible all by itself. It's the only time that's ever happened. The Soviets attempted this back in the 70s, didn't even work once. But that worked. Separation worked. Things went poorly for the first stage after that. The upper stage essentially got to orbit, but then there was some other issues going on and they weren't quite sure of the control of it. And when you have something that's 1,000 tons and going to re-enter somewhere, you disassemble it as high as you can so that the bits are smaller as they come back down. Although if you go searching on the YouTube, you will find a beautiful video of a guy from the Dominican Republic showing that nose cone assembly. This upper part right up here with those fins, almost intact, tumbling end over end through the sky. And then it found the water with vigor, as they described it. To make it a fully reusable rocket, what you're talking about here is the first stage takes off, and after about 2.5 minutes or so, separates. The upper stage then continues to orbit. The first stage then flips around, flies back, and lands. Which sounds insane until you realize they've done it with a Falcon 9 250 times already, to the point where it's actually boring. This is a much, much larger rocket. The Falcon 9 is 3.7 meters diameter. This is 9 meters diameter. The weights are astonishing. And he doesn't even want to land it with legs. He wants to catch it with a pair of giant steel chopsticks, because that's not crazy. Then the upper stage goes into orbit, does its business. It has about 100 tons of payload, which puts it in the Saturn V class, so it's some of the biggest rockets ever made. And after it's finished its mission, it has a heat shield, so it's capable of deorbiting on its own. Belly flopping through the atmosphere, and then when it gets back to the pad where it's supposed to land, does a kick flip, lights the engines on its bottom, and lands on its tail, just like Buck Rogers. And that would be insane, except they've already demonstrated it once. If this works, and to be clear, it doesn't work yet, the price to orbit drops by another order of magnitude. So these days, well, back in the old days, actually, the Atlas V, which is a rocket that's now essentially retired, ran about 25,000 a kilo. That's when they didn't have Falcon 9 around. When Elon got Falcon 9 up and running, he drove the price down under, it's actually lower than this now, close to 3,000 a kilo, which is a bargain for rocketry, enough that it made everybody else try and get better. Vulcan's now flown once, but those numbers are still speculative. New Glenn has never flown. The Space Launch System, that's the Artemis rocket, which is derived from the space shuttle, is just about the most expensive way to put anything in space. And you can tell why, because it was demanded by the US Congress. And if there's anything American politicians are good at, it's wasting money. Starship, depending on who you ask, somewhere between $25 and $200 a kilo. I mean, that now puts it into the realm where you could ride it for the price of a first-class ticket to America. That's pretty big opening into space. Lowering that price just sort of says, okay, we can put a lot more stuff up there. Plus, the payload space is massive. It's a 9-meter diameter space, and up to about 100 metric tons, might be more as the improvements go on. So you could lift the International Space Station with those dimensions in 4 flights. It took them 15 years to build this thing in about 60 flights. So just trying to get, if there was a Starship here, it would block most of this. It's 60 meters tall. This thing's only 120 meters long. So Starship is really very big. We're looking for commercial aspects in space. And as much as you can make fun of NASA, and it's easy to do, they have pushed pretty hard to commercialize space. The International Space Station is not a commercial entity by any stretch of imagination. It's a research station with a series of international agreements to make it happen by making a deal with the Russians and the Europeans and the Japanese, and even the Canadians are in there. They basically made it impossible for our American president to cancel. It's covered in international treaties. It's a game that NASA plays to make sure that stuff actually gets built. And it worked. But they also, through the actions of certain members, started contracting out parts of the space station, starting with resupply. That's the original product that Elon Musk made money on with SpaceX, was to bring supplies to the space station. And rather do normal cost-plus contracting, where they pay whatever it costs to get up there, plus a bonus if you can get it done on time, which does not drive prices down. They said, hey, we'll pay this much per ton for lift up and this much per ton for lift down. How you do it's up to you. And so you make more money if you get more efficient. And they did. And so now resupply of the space station has never been cheaper. They've now moved crew motions over to that same system, to the Crew Dragon. So now crews are moving up and down for dramatically less. The average, when they were doing resupply for the space station with the shuttle, they were running somewhere in the neighborhood of $1.5 to $2 billion per flight. And that would give you about 5 metric tons of supply and 4 astronauts that you could leave behind. Today, a cargo Dragon runs about $65 million for about roughly the same supply, and a Crew Dragon runs $120 million. So way more efficient. And this thing is old. There's lots of mistakes in it. As much as it's one of the most complex machines ever built and one of the most expensive projects ever made, it's got a deadline. It's about 2030. Before there's enough parts worn out on it that it's just not safe to operate anymore, and they intend to deorbit it, which is also a problem. It's very heavy, and getting it to land safely, which is to say in a fiery debris that lands in the ocean rather than on people's heads, they actually haven't quite cracked that problem yet. They know what they need to do, but they have to build vehicles to do it. But NASA's back at it again with their commercial space stations program. So they've essentially said, we're not going to build another space station, but we will buy time on space stations. Here are the specs of the stations that we would look for. So their goals have more, smaller, specialized stations owned commercially, renting time on them. So this is more about building out an economy in orbit. This is an opportunity to do factory work, to do different kinds of experiments. The laboratories on the ISS were built specifically for human-based microgravity experiments. We've learned a lot about how poorly humans do in freefall. We understand that very well now. And that's because of that laboratory. There's a bunch of other experiments we'd like to do, but they're not compatible with what the ISS does. And so making smaller stations allows us to have dedicated workspaces for that. And a bunch of companies have proposed different approaches to it. Some of them will actually go ahead. These are early days yet, but a few folks are actually bending metal. The Jeff Bezos one is huge. It's based on their New Glenn rocket. And we hope it'll exist, but they call this orbital reef. This is actually 3 of their systems combined, so that would be bigger than the International Space Station. Each one of those inflatables represents almost the entire volume of the space station. One of my favorite technologies that's coming out of this thing is a little rover. So right now, if you want to go into space, if you want to do a spacewalk, it's about a 6-hour endeavor. You have to pre-breathe oxygen to be in the lower pressure. It takes 2 people to put your suit on and so forth. Like, these guys go through a lot to spend 8 hours out there in their little portable spaceship. This is a quick way to do it. This runs at normal station pressure, so you basically slip through an airlock, lock the bottom behind you, disconnect from the station, zip around to the area you need to work, use manipulators, do your thing, but you're at least right on site. I don't know why these don't already exist, but they're part of the proposal for the commercial space station. A few other designs. This is the inflatable done by Lockheed Martin. This one's got a little set of drones around it for controlling it. So these are all new proposals going beyond the space station. And then there's Axiom Space. These are ex-space station guys that have now gone on the commercial side. They're actually building this first component here. The metal is bent for this. They expect in the next 2 years to add it to the International Space Station. They want to build out a free-flying station connected to the space station. And then after the space station is gone, or is ready to go, they'll separate off and be an independent station. So that's furthest along. They're actually bending metal. So there's activity going on in low Earth orbit that's moving towards more commercialized space, and that makes us more sustainable up there. It's not just expensive programs down from Earth supporting up there. It's finding products and opportunities up there that can allow us to create more activity in space. Let's move on to the moon. This is my favorite picture of the moon. Why? Well, look, I fight against what's science fiction and what's science fact all the time. And the first thing you have to ask when you see a picture like this is, who took this picture? Because that is a picture of the far side of the moon. Notice it's not the dark side of the moon. It's not dark at all, although actually it appears darker than the side of the moon that faces the Earth. The moon actually rotates, it is gravitationally locked to the Earth, so the same side always faces the Earth as it goes around. This is the side that doesn't face toward the Earth. This picture was taken by the Deep Space Climate Observatory. This is a satellite actually meant to study the sun. And so it sits in a stable Lagrange point between the Earth and the sun all the time. And somebody was clever enough to put a telescope on the backside of the satellite. And it is a telescope because the Earth is 1.5 million kilometers away from the satellite. So it's very small. And it routinely takes pictures of the full disk of the Earth because it's in that Lagrange point. It always has a full view of the Earth. And so it makes a great time lapse of the Earth doing its thing. And every so often, the moon whizzes through the shot and whizzes. Like if you look at the rate that they're taking pictures, there's only maybe a dozen frames where you see the moon go humming by. Also, this it's not actually a color camera. It's a monochromatic camera that has color filters. So they actually have to take 4 pictures to make a color picture. And it's one of the ways you know this picture is real, because if you get really close to it, you'll notice that right on the right edge of the moon there's a green haze. And that green haze is because the green filtered photo is taken last and the moon moved. So, but it's a unique picture. Like, it just reminds us, like, and it's, it's so, the Earth's so bright, there's no visible stars in a shot like this. Now, we've been to the moon. People wonder why we'd ever go back. We had the Apollo missions back in the day. This was a competition between the Soviet Union and the United States of America to see who's dumber. 12 white men walked on the moon, 11 of them test pilots. 1 scientist walked on the moon. This guy right here. That's Jack. Harrison Jack Smith was a geologist. He actually trained the test pilots on how to find important rocks on the moon. That's a very difficult thing to do because most science isn't done by Eureka, I found it. It's more, what the hell is that? You need to know all the normal rocks to be able to recognize an abnormal rock. Schmidt had originally been scheduled for Apollo 18, but Apollo 18 got canceled. And so they moved him on to Apollo 17, and he got to go to the moon. It's the only time we ever put a scientist on the moon. This is Jack. You will notice Jack is extremely dirty. Jack is a geologist. Geologist likes rocks. And he's looking at rocks that nobody else has ever looked at. So he fell down a lot. And he's just covered in dust. He also found that the gold reflective eye protection was annoying him. It was changing the color of the rocks. So he kept flipping the visor up so he could see what he's doing. Now that visor is there for a very important reason. There's completely unfiltered sun bearing down on them. And if he was to look at the sun, his eyes would immediately die. And the upside to him flipping that visor is we have one of the very few photos of an actual face on the moon. That's Jack on the moon with his visor up. All of the Apollo missions, by the way, are on YouTube if you want to go and watch them. And you will hear the NASA commander repeatedly say to Jack, "Hey, Jack, when you get a sec, can you put your visor down? You dumbass." But Jack wanted to look at rocks, and so he kept lifting up his visor. One of the ways he tried to protect his eyes, you can see it in the helmet here. See that white stuff there? So he's taking the mission cards, what they're going to do every minute that they're on the moon, and as he finishes them, he's ripping them off his wrist, and he's sticking them in his helmet to protect his eyes so he can flip up his visor to look at rocks. This is what happens when you put a scientist on the moon. There's a certain species of human that is wired to explore, and they're not test pilots. You ask the test pilots, what were you thinking when you were on the moon? And they mostly said, God, I hope that I don't screw this up. That was the main thing they were thinking about. And they didn't screw it up, right? All of them managed to come back. What was Jack thinking about? I can't wait to see the rocks. If we put these kinds of people up there, what do they find? Jack, in the 3 days that he was on the moon, found more important rocks than the rest of them combined. He found a piece of unshocked olivine. Now, this is how I know you're not geologists, because if you'd heard, he found unshocked olivine on the moon, you go, holy cow, that's incredibly important, because it is. Olivine is only formed in volcanic eruptions, except when asteroids impact. Then it creates shocked olivine. He found unshocked olivine, so it was proof that there have been eruptions on the moon. It's important. And only a guy who knows what is weird could find it. That's what a scientist is for. They know the difference. We've only done it once for 3 days. Yeah, he might fry his eyes, but to a worthy cause. He knew this was it. This was the last mission to the moon, and he was going to make a difference, and he did. One of the main reasons they canceled the Apollo program was this thing. The lunar lander was the edge of technology of the time. It's the 1960s and 70s. This is a dangerous machine, actually. There were so many failure modes on it that were unrecoverable, that if anything went wrong, those guys were dead. There was just no way to get them back. You know, there was, if it worked perfectly, it only had 3 days worth of supplies from on it, and it took 3 days to get there. Like, you're not going to be able to get them back. And remember that this was a military mission, actually. That's why it's mostly test pilots. Their goal was to prove that American technology and capability was superior to the Soviets, and every day that they continued to do that, they risked screwing it up. So they stopped. But it's 50 years later, and the technology's better. And so the Artemis project, and Artemis was the brother to Apollo, or the sister to Apollo in Greek mythology, is about revisiting the moon, this time with a little more sense, a little more technology, with the idea of actually staying. So we've flown one Artemis mission so far. It was unmanned. We did a lot of orbital experimentation here. We have much better computers, much better understanding of gravitation in orbits today. They did tricks with Artemis 1, never been done before. But it wasn't particularly exciting to people, to the rest of the world, because there's no people involved. It's just a test flight. The next flight, Artemis 2, is going to have people on board. They're going to fly around the moon and come back. Very Apollo 8. Seems very retro, but they don't have a working lander, so they want to get them up there. There are 4 of them. One of them's a Canadian, the other 3 are Americans. This was supposed to fly this year, and it's already announced to fly next year. So the SLS is an expensive rocket. It's about $2 billion a shot. It's kind of impractical, but it's the one that their Americans have to use. And then Artemis 3 will be the first landing mission. So this is where they now have a dedicated lander, preferably a reusable lander that will actually put on the moon. The current front runner for building the lander is Elon Musk. He wants to take a modified version of Starship and land it on the moon, because a 60-meter tall lunar lander is a good idea. Like, land on a flat spot, be careful. And also the bottom 3/4 of this, This is all fuel tank down here. So the people are up here. So notice the elevate, like watch that first step. The moon hasn't got a lot of gravity, but you're gonna build up some momentum. So, and you can see how small the people are down here. There they are.
Just throw a cushion on the bottom.
Be careful. Yeah, we could talk about this design, but they are the furthest along. It's fully reusable. It carries 100 tons. Like there's a lot that's good about it. One of the downsides too is it needs refueling. They'll burn most of its fuel getting into low Earth orbit. Then it's going to need fuel to actually get to the moon, land on the moon, get back off again, and so forth. And so in the actual mission complex, you're going to have a series of flights to refuel the spacecraft to even make this thing work. So they got to make tanker versions of Starship as well. Now, if it's a fully reusable rocket, that's not that big a deal. Fuel is cheap. Flying's expensive. But if you don't have to throw away the rocket each time, this may well make sense. Couple of little problems. We have never refueled a spacecraft, ever, in orbit. It's an untested technology. This was one of the proposals. It's vaguely inappropriate. What's the issue? Well, the issue is that when you're in free fall, the fuel floats around. Here's a video. So this is the inside of a Falcon 9 liquid oxygen tank. It's currently under power. It's going into orbit. So this is a camera looking down. You can see the moment they turn the power off. It's hard to pump it when it's floating around like that. You need it to all sit at the bottom of the tank where the holes are so that you can pump it out. So you need to be under acceleration at all times to move the fuel around. So you can imagine, I mean, this one also seems vaguely inappropriate too, right? Two of them docking together, but then they have to accelerate, which changes their orbit. One of my favorite ideas for actually doing refueling is to actually build a rotating structure. So Eric Berger drew this. So you dock a set of them, they're balanced, and then when you need to pump fuel, you spin it. And that sends all the fuel to the bottom of the tanks. Now you can pump your fuel around. This also speaks to the idea of first you put up all the fuel tanks, then you fly the lunar lander up here, refuel it all at once, and then off you go. So no waiting. This also speaks to another commercial interest. Because you're also going to probably need one of these around the moon. So if you put a couple of these up in orbit around the Earth, now you just put a price out for fuel. If folks want to get innovative on different ways to extract fuel from elsewhere on the solar system, here's a market for it. Get it to here, we'll buy it. So you can supply it yourself, or you can put it to a more open market for that. This is a cool idea. It's not been built yet. It's been talked about many times. I actually dug out this old drawing from Lockheed Martin from the 1990s about building a depot based on the upper stage of an Atlas V with a heat shield and so forth. Although in this case, they're trying to store liquid hydrogen, which is virtually impossible. So we were talking about being on the surface of the moon with our 50-meter tall rocket. Make sure you keep it level, step carefully. Now we get to do some experiments, right? We don't have good suits yet. The lunar surface suits that were built back in the 60s are archaic. They also had a running time of about 3 days, which is good because it was as long as the missions were. The moon's regolith is incredibly abrasive. It gets into absolutely everything, and it wears. It does damage to joints and so forth. We're trying to make suits now that will last 800 hours when the current record is 22. So that's part of the many missions. Actually, the weirdest thing in this photo is the fact that this person is kneeling. The suit's pressurized. If you ever watch the astronauts walk around the moon, they kind of do this, Michelin man wobble. It's because bending your knees is virtually impossible because the suit's under pressure. So the idea that they would be able to manage pressure around joints so that you're more flexible, you could actually bend down, kneel, stand back up again. When the astronauts fell down, they would just push off their hands and sort of bounce into the air and try and land on their feet. They sometimes got it wrong and tipped over backwards, and it's hard. You only got 1 6G. That lunar lander on the left there is a proposal by Blue Origin and Draper. It's a 3-module lander that leaves behind a descent stage, which is not a good way to reuse. You have to basically build a new lunar lander every time you want to do a landing. And if you're going to pick a site to hang out on, you're going to leave these things behind. So we need a reusable lander. It's a very hard problem, and we haven't solved it well. Where do we want to go on the moon? In Apollo, we mostly landed near the equatorial regions because we had limitations of the spacecraft and we wanted to always be in view of the Earth. But the resources that we think are interesting in the moon are on the poles. So one of the proposals is an area around Shackleton Crater along the southern edge of it. It's almost directly on the South Pole, and parts of it are continuously lit and parts of it are continuously shaded. There's an animation of this. That's the Shackleton Crater on the moon. And you should ask the question, who took this picture? This is a composite of photographs taken by the Lunar Reconnaissance Orbiter. It's been in orbit around the moon since 2009. And every time it flew over Shackleton, it would take another picture. And then they assembled it into a multi-year long time lapse to show how parts of the crater are always lit and parts of the crater are always dark. The dark parts have ice, the light parts have solar power. So if we logical place for us to build a base where we have access to resources of both kinds. And the Indians recently landed a small lander and rover near this area. They're the first to land on the South Pole. Navigating on the moon is difficult. We don't have GPS up there yet. We also don't have good communication systems up there yet. South Pole's not always in view of the Earth. So ESA has a proposal called Moonlight, where they will put an array of about a dozen satellites in various tundra orbits or long elliptical orbits. So that at any given time, a spacecraft will be in view of 3 of them, which allows them to navigate precisely, know where they are over the surface of the moon, and cellular communications. So rather than have to haul all that navigation gear and long-range radio gear on your spacecraft, you now can depend on infrastructure. So bit by bit, we build out space stations, fuel depots, relay systems. This is infrastructure to make it easier and easier for us to spend more time on and around the moon. Lots of proposals for moon bases. This is the one Elon came up with. I thought everybody immediately looked at this and thought Burning Man, which is not appropriate. I thought Space 1999. You remember that? Nobody old enough anymore. If you may remember this from your childhood, do not go back and watch it. Your memories of it as a child are vastly superior to the actual show. Just don't wreck your childhood. But far more realistically, and this is from the original ESA proposal, is small habitats like igloos that they use robots to bury in the regolith to protect from radiation. They give a safe spot for astronauts to function in. Longer term, we're probably going to look at lava tubes. This is called the Marius skylight. So there was volcanic activity on the moon. Our friend Jack Smith proved that. And when the lava flowed, as it cooled and withdrew, it left behind these massive tubes, in some cases more than a kilometer in diameter. And this is called a skylight because at the point where the tube was so close to the surface that the roof collapsed. The drop in here, they think, is about 400 meters. But if you were able to get up to the edge of that, bring a couple of inflatable space stations with you, slide them in underneath that tube and inflate them, you've got a built-in radiation shield and a great big space to work in. So another a way for us to be up there. It's not as sexy as all those, cool Burning Man kind of things, but it's practical. And it allows us now to function for an extended period on the moon. What do we do while we're there? Well, collecting rocks can be fun for a while, but really we're about resource extraction. So now we have to get into things like surveying, assaying, mineral extraction, mining and refining, building machines that function on the moon to find the useful ores. We already know that there are large concentrations of silicates, iron, calcium, titanium, magnesium, phosphorus, various kinds of radioactive thorium, uranium found in concentration up there, magnesium and potassium, rare earths are there. So if you can round them up, you have a little bit of gravity to work in. The funny thing is if you actually look at the list, it's all the materials that go into certain products. One of the classic ones is solar panels. Everything we need to make solar panels is on the moon. One would argue, because with contemporary solar panels, these silicon carbide solar panels, these are big crystals. And crystals grow better in lower gravity. Like we may actually be able to make superior solar panels on the moon than we can make here because the lower gravity will benefit us. Now, we need those solar panels on the moon, right? We could literally carpet chunks of the moon in solar panels, relatively cheap to do. A lot of robotics on that, and we have plenty of power. But it's also a product we can send back to Earth, although I wouldn't send it back to the surface of the Earth. Now, one thing that's nice about the moon is the gravity is pretty low. You only need about 2 kilometers per second of delta V to get back into orbit, as opposed to the Earth's 12 plus dealing with atmosphere. So you can largely fire stuff up with linear accelerators. You don't actually need a whole lot of rocketry to do this. And we could take those solar panels, we could send them back to the Earth, and you can just see barely around the Earth there, this little margarita glass looking thing. That is SPS alpha. That is a proposal for space-based power. So rather than generate electricity on the surface of the Earth, let's generate it in geostationary orbit. You make your solar, the only problem is that these are several kilometers across to make a gigawatt of power. There's only 1,320 watts per square meter of light coming from the sun in our low Earth orbit. Less gets to the surface, less than a kilowatt. So we get more up here, but we have to make it big. It's just big. And so it's too expensive to lift all that stuff from the Earth. It's $1 trillion project if you want to try and lift it from the Earth. But if you could build it on the moon, it becomes a multi-billion-dollar product. It becomes actually roughly the price of a major power plant on Earth, if we have the infrastructure already built on the moon. And that can put about a gigawatt of power back down on the Earth through about a 10-kilometer wide rectenna array. Now, these are microwaves. You shouldn't hang out in there. There should be a fence around this. It won't actually cook birds in flight. Like, that's okay. That's not a problem. Aircraft should avoid. It's not as cheap as, towards the equator, things like solar and wind and pumped solar and pumped hydro. We can produce power fairly cheaply with low emissions. But more towards the poles, emergency operations, being able to put it down in different places that need it. Military operations, the military is very interested in that. You think about just how much gasoline they shipped into Afghanistan over the decade that they were there, where they could have beamed a gigawatt of power down and run electric on everything. But actually, it's not the most interesting part about building a system like this. Using it in space is actually more interesting. Every rocket has the same problem. You have to carry a power plant, fuel, and an engine. Especially when we're talking about going back and forth between the Earth and the moon. What if we just left the power plant in place, beam the power to it? So the proposals for microwave-based spacecraft already exist and have been tested. We know how to transmit microwaves. Now, we're not actually pressing against the spacecraft the microwave. What we're doing is we're turning the microwaves back into electricity and we're running the engine with it. So rather than carry a heavy power plant around or a huge bunch of solar arrays, you carry a very light microwave rectenna that superheats the fuel for an ion engine. So that makes your vehicles lighter, makes them run more efficiently, and you get to just target the energy where it's needed. So you accelerate up to speed, then you move on to the next workload. So you build a few of these around in orbit, you've just lowered the cost of maneuvering around the Earth. We could put more of them, larger ones. We could switch to lasers. There's a bunch of experiments that can be done there. But building out that infrastructure provides electricity for a bunch of different services, and electrical-powered spacecraft are pretty useful. I could now go into nuclear-powered spacecraft, but I'm not going to. Because there's a lot of problems with it that it's hard to have that conversation. It's great in science fiction. It's not so great in science fact. There's so far no way to make a nuclear-powered engine that doesn't stay radioactive and kill everybody. Doesn't mean we're not researching it. We are, but we're not there yet. Let's talk about the next problem. One of the things we've learned in the International Space Station is that humans are not good in free fall. We only leave them up there typically for 6 months. It takes them over a year to recover when they come back down. The bottom of their feet hurt because they haven't used them for 6 months. Peristaltic systems work fine in free fall. Your blood pumps, you can breathe, you can eat, but you can't burp because food floats around. Burps get dramatic. Although there's actually a great video of guys on the space station showing how to burp, which involves backing up against a wall, then pushing off so that all your food settles, and then you can burp. And if you get it wrong, you have to clean it up. But the main problem is cerebrospinal fluid. So there's a pair of organs inside your brain that produce a fluid that your brain is bathed in that largely clean your brain. They take the detritus away from your brain, and it runs down into your spinal cord where it's exchanged with your blood system to go to your kidneys. But there's no peristaltic pumps in that. It's literally based on gravity. And nurses know that with bedridden patients, you have to sit them up every day, or people's faces swell up and so forth. And it's to move that cerebrospinal fluid around. Well, in free fall, the fluid doesn't move around. It sits in the head. And so you'll notice astronauts get kind of puffy. And they all are wearing glasses when they're in orbit because that fluid builds up so much it presses against the backs of their eyes and bends them. So they have sets of readers depending on how badly bent their eyes are at any given time. And it causes long-term damage. Plus bone degeneration. They're exercising 2.5 hours plus a day. just to maintain their body well enough that they'll be able to recover 6 months later. It begs the question, like, how would you fly to Mars in a free fall spacecraft? It's going to take you about 6 months to get there. And there's nobody there to help you when you land. I think that's an Elton John song. Wait. Anyway, we need to experiment with centrifuges. It's the only way we know how to make artificial gravity. In science fiction, we make all kinds of artificial gravity, but we do know if we spin a structure, it creates sufficient gravity to be useful. The thing is, we've never built anything big enough. There's a great graph here that says how big you need to be versus how fast you rotate to create sufficient Gs without a Coriolis effect, the difference between the gravity at your head versus your feet, making you nauseous and off balance. So it has to be fairly large, and we've never built anything that big. There was a proposal to put a centrifuge on the International Space Station, but it would mess up all the microgravity experiments, so they never did it. It's one of the reasons to go to multiple space stations if you want to start building centrifuge stations. There's also a question about how much gravity do we need? 1 G makes this really hard. Third of a G, substantially easier. We just don't actually know how well the body would do in a third of a G. We've never done it for an extended period, which, by the way, is another great experiment to do on the moon. That's a sixth of a G. So now we could put somebody up there for 6 months to see how they do at a sixth of the G, then going back to regular gravity. There's been all sorts of proposals for creating rotating structures on spacecraft. This is one called Nautilus X. It also has a nuclear power plant in the back, so we can debate the relative value of that. But you need that rotating structure. In science fiction, I think the best example of this was the Hermes from The Martian. There's a lot of things that are dumb about The Martian. The Iron Man thing being one of the worst. Although also a storm that blows you around on Mars is ridiculous when there's no pressure there. But this vehicle's pretty good. It's got nuclear power in the back. Most of these are actually heat radiators for that. That's fuel system for that. Lots of concerns there. This is all the zero G parts of the spacecraft, so they're all free fall. Although often in the movie they were sitting in here and it looked like they were sitting down just fine. This is the rotating structure. So notice they've built a wheel, and it's big, probably pushing 60, 70 meters across, but they didn't make it solid. They made a set of compartments. And you go between those compartments by going into the center, which would be back to free fall, and then out on the edges. But I think the most important thing, and again, we don't actually know this because we haven't done the test yet, is if you were sleeping in gravity every day and then you could work in zero G, would you be okay? There's a few challenges with that. One is virtually every astronaut, when they first go into free fall on every trip, even the ones who've done multiple, are nauseated for a day before they get their space legs. So if you keep going back and forth between gravity at night, are you just nauseated every day when you're working? Like, that could get old. But maybe we'll acclimate to that. So, but we need a rotating structure. These are the experiments that need to happen to know more about what we can actually do to have humans in space for an extended period of time. All right, coming into the end of this, let's talk more about asteroid mining, because this is where we make an economy, right? We've made economies around fuel, we've made economies around experiments, mineral extraction on the moon. Learning those things brings us to the ultimate resource, which is these asteroids. This deals with a whole bunch of problems. This is helping to protect us, provide additional resources, provide workloads, make valuable things up here. Mining asteroids is tricky. They have very little gravity. But they're also not organized like ore bodies are on the Earth. The Earth has geotechnic motion that tends to concentrate bits of ore together. They get formed, and so you can mine them out of the rock. Most rubble pile and different types of asteroids, it's sort of blended all the way through. Now, there's a bunch of research that's been done in that area. There's different companies that propose things. This is something called the honeybee. So the honeybee captures a relatively small asteroid, maybe 30 meters across, in a chamber, closes it up because they're going to break it apart and they don't want the debris to fly everywhere. Then they use these helio collectors, big eyeballs that collect sunlight and direct it down a central shaft, and they vaporize the asteroid. Now, the reason to do that is you want your volatiles out first because water's incredibly valuable. So they've got collectors around it, so as the water vaporizes, it'll actually freeze back on different surfaces, so you can conduct that flow into containers, separate out the water, do some additional cleaning. You can split that into liquid hydrogen and oxygen. There's a bunch of products come from there. Carbon's also highly available if you want to make methane. So carbonic asteroids are valuable. And then you get into the mineral part. So same thing, superheating, chemical separation, crushing and processing. You don't want to move the asteroid. They're heavy and they're mostly worthless rock. Silicates are too cheap to move and they're heavy. So you'd rather extract the rare earth materials and the platinum classes and the volatiles. So you do that in situ and you basically turn it into gravel when you're done, taking all the valuables out. You put them in these tanks and you send the tanks off to do your work. There's lots of variation on this. Lots of experimentation has been done. They've built pieces of this. So you can imagine building a bunch of these. They're not insanely huge. They're big, 30, 40 meters, 50 meters across. The number of asteroids available in that space are huge numbers, huge volume of it. And you collect the materials and then you put them to work. Now, some of them you're going to send back to the Earth, right? That was part of the deal here. It's a fairly expensive way to get minerals back on the Earth, but as certain materials become rarer on the Earth, having a supply from elsewhere will be justifiable. But the far more important thing is to then start utilizing them in space. A spacefaring civilization makes its own stuff, not in the gravity well, right? The gravity well is the enemy. So you can imagine, yes, very science fiction-y picture. But you're at a point now where you're bringing in materials from different asteroids and starting to assemble from those materials. So construction in space. Where do the people end up ultimately? Knowing that gravity wells suck. Once you have all this stuff nailed, you're able to prospect asteroids, go to them, mine them, refine from them, collect materials, do construction. First spacecraft built in space is going to be pretty cool. Next logical step is to start building habitats. Occupying planets is kind of dumb. You put all this effort into going into orbit. Why are you going to go back out of orbit? Stay in orbit. So an O'Neill cylinder comes from the 1970s. And it's the proposal to build large cylinders in space out of space-based materials, rotate them for gravity. Kilometer across, 8 kilometers long. Solar collectors for energy and to reflect light in so the light looks fairly natural. So you're living in a tube, but city scale. And if you want to go to space, you take an elevator. You go back up to the central axis, out to that ring structure here, and that's free fall. You're ready to fly away. You don't have to waste a lot of energy getting off where you want to go. These will hold a couple million people. Build as many as you like. Now, are we going to depopulate the Earth into O'Neill cylinders? No. That's not how that works. Immigrants don't populate the new world. Immigrant children populate the new world. So, yeah, you'll send out a few folks there. They will be fruitful and multiply. But you will also build some redundancy for hopefully these soon-to-be self-sustaining colonies as they collect their own resources. And other places to create science. And you might have a rebellion or two. That happens. But you know how many of these you can build? Tens of thousands. Many more people could live on O'Neill cylinders than can live on the surface of the Earth. And then we're living and operating in space. We haven't even done the fun stuff. I've just been playing around the Earth. You should see some of the other orbits we could be in. The fun things happening out in the gas giant area, or in around Venus, where we have far more solar power. And Venus is a great planet. Don't go to the surface; it's a little warm. But around 75 kilometers up in its atmosphere, you hit a point where it's about 1 G of gravity, twice as much solar energy, and gases you can collect for power and resources. There's a lot for us to exploit, and all based on this set of skills. So. I've been pointing out to you a bunch of the things we've already done to get to this place. This now feels like science fiction, but there's a direct path to this place for the things that we're doing today. And I'm hopeful. We don't only have a certain amount of time, but the next few decades, we'll see most of it. If this was fun for you, the link geekout.show will take you to the .NET Rocks site with just the Geek Out episodes. There's about 100 of them. I make a couple more every year. Thanks so much for coming out.